Hello everyone and welcome back to the statistics video lecture series. Today we are going to be covering another topic of probability called the addition rule. So before we get into what the addition rule is and what kinds of probabilities it does apply to, we need to talk about something called mutually exclusive. So mutually exclusive events, we're dealing with two events again. Two events A and B are mutually exclusive if A and B cannot occur at the same time. So if there are absolutely no instances in which event A and event B could occur at the same time, they are called mutually exclusive. Now, if there is any overlap between events A and B, and if A and B can occur at the same time, then the events are said to not be mutually exclusive. So these little Venn diagrams just provide a visual of what mutually exclusive is. So this circle here represents all of the outcomes in event A. This circle here represents all of the outcomes in event B. So these two circles do not overlap, which means that there is no chance of A and B occurring at the same time. If A and B cannot occur at the same time, they are called mutually exclusive. On the flip side, for this other Venn diagram, circle for event A and the circle for event B do overlap, so there is a section where A and B could occur at the same time. Because these two events could occur at the same time, they are not mutually exclusive. So what we're going to do is we're just going to practice determining whether two events are mutually exclusive or not mutually exclusive. So when you're determining this, you should always ask yourself, could these two events occur at the same time? Is there any overlap between these two events? If there can be overlap, if they can occur at the same time, they are not mutually exclusive. If they cannot ever, under any circumstances, occur at the same time, they are mutually exclusive. So for number 1, event A is rolling a 3 on a die, and event B is rolling a 4 on a die. And even though it is implied it's six-sided, regardless of the type of dice you have, there is no die in, there is no most normal die do not have both a 3 and a 4 on it at the same time. So one side of a die cannot read 3 and 4 at the same time. So because these two events cannot occur at the same time, they are mutually exclusive. So for number 2, event A is randomly selecting a male student, and event B is randomly selecting a nursing major. So you have to ask yourself, could these two events occur at the same time? Can you have a nursing major who is male? Yes, you could have a person who is both a male and a nursing major. So because of this, these two events could occur at the same time, so that means they are not mutually exclusive. And then for number 3, event A is randomly selecting a blood donor with type O blood, and event B is randomly selecting a female blood donor. So you have to ask yourself, could these two events occur at the same time? Could you have a blood donor who has both type O blood and who is female? Yes. So since these two events can occur at the same time, they are not mutually exclusive. So determining whether or not an event is mutually exclusive is essential when you're dealing with probabilities of one event or another. So the addition rule is going to apply to the probability of event A or event B. So this is very different than the multiplication rule, which was dealing with A and B in a sequence. So this is, what is the probability of this event or this event occurring? So the probability that events A or B will occur is given by the rule the probability of event A plus the probability of event B minus the probability of A and B. And this rule is assuming that they are not mutually exclusive. So if the two events are not mutually exclusive, what is happening here is for the probability with or, you take the probability of the first event and you add to it the probability of the second event. But if the two events are not mutually exclusive, they could occur at the same time. So by just adding them together, you are inadvertently adding that probability of them occurring at the same time, more than once. So what you have to do to compensate for that is you have to subtract the probability of the two of them occurring at the same time. That's what this probability of A and B is. That is the probability of A and B occurring at the same time. So it's the probability of the first event plus the probability of the second event minus the probability of the overlap. Now, if the two events are mutually exclusive and there is no overlap, then all you have to do for the probability of A or B is simply add the two probabilities together, probability of A plus probability of B. And if you have more than two mutually exclusive events, you can just keep adding their probabilities together. And so that rule can be simplified to any number and extended to any number of mutually exclusive events. So just to recap, if you're finding the probability of A or B and the events are not mutually exclusive, you take probability of the first event plus probability of the second event minus probability of the overlap A and B occurring at the same time. If the events are mutually exclusive, then the probability of A or B is probability of A plus the probability of B. So anytime that you're doing probabilities involving or, you do have to ask yourself, are these events mutually exclusive? Because whether or not they're mutually exclusive will determine if you have to do any subtracting or not. So for number 1, you randomly select a card from a standard deck of 52 playing cards. We're going to find the probability that that card is either a 4 or an ace. So I want to point out that unlike the previous video with the multiplication rule, that was 2 events occurring in a row. Only one card is being drawn here. You're just selecting one single card, and you're just finding the probability that that card is a 4 or the card is an ace. But only one card is being drawn. All right, so the first thing you have to ask yourself is this event mutually exclusive? Can you have a card that has both a 4 on it and an ace on it? No, cards, 4 or ace, there is no card that has, multiple numbers on it. It's just a 4 or it's just an ace. So because these two events cannot occur at the same time, they are mutually exclusive. I'm sorry for the amount of glitching that's going on with the stylus today. So because these two events are mutually exclusive, all you have to do is add their probabilities together. So we're going to find the probability of selecting a 4 at random, and we're going to add to it the probability of selecting an ace at random. So the probability of selecting a 4 at random, out of 52 cards, 4 of them have a 4 on it. Then we're going to add to it the probability of selecting an ace. So out of the 52 cards, there are 4 of them with an ace on it. Remember, only one card is being drawn, so you don't have to worry about is the card being replaced. There's just one card being drawn, so we're finding the probability that it's a 4 or an ace. So 4 out of 52 plus 4 out of 52 is 8 out of 52, or 2 out of 13, or if you want to turn it into a decimal, 0.154, or approximately a 15.4% chance that the card is either a 4 or an ace. So then for number 2, we're going to roll a 6-sided die, and we're going to find the probability of rolling a number less than 3 or rolling an odd number. So we are finding the probability of rolling a number that is less than 3 or rolling an odd number. So the first thing that you have to ask yourself before you go finding any probabilities, are these events mutually exclusive? Can these two events occur at the same time? So picture a 6-sided die. Is there a side on that die that has a number that is both less than 3 and an odd number? Yes, there is a side that is both less than 3 and odd. So the side that has the 1 on it, is both less than 3 and odd. So because 1 is both less than 3 and odd, these two events are not mutually exclusive. Because these two events are not mutually exclusive, that means we're just going to take the probability of the first event plus the probability of the second event minus the probability of the two overlapping. So we're going to take the probability of the first event, the probability of rolling a number less than 3. Then we're going to add to it the probability of the second event, probability of rolling an odd number. And then we're going to subtract from it the probability of the two events occurring at the same time. The number that was both less than 3 and odd was a 1. So because the side that has the 1 on it was the overlap, we're going to minus the probability of that overlap. So we will subtract the probability of rolling a 1. So for the probability of less than 3, out of the 6 total sides, 2 of them read less than 3. Plus the probability of rolling an odd number, out of the 6 sides on a die, 3 of them have an odd number on them. Minus the probability of the overlap. So out of the 6 sides, there is only 1 of them that has a 1 on it. So when you do the subtracting and the adding from left to right, you get 4 out of 6, or 2 out of 3, or a 0.667 chance, or about a 66.7% chance of rolling a number less than 3 or odd. So you always have to determine whether the events are mutually exclusive whenever you are dealing with probabilities involving OR. So for this next one, this is an example of empirical probability. This frequency distribution shows the volume of sales in dollars and the number of months in which a sales representative reached that sales level during the past 3 years. 3 years is 36 months. You can also figure that out by just adding all of these months together and you get 36. Using this sales pattern, we're going to find the probability that the sales representative will sell between $75,000 and $124,999 each month. So first, let's take a look at the frequency distribution. This is the class that has the low end, that's $75,000, and this class here has the high end, the $124,999. So these are from 2 different classes. This range of dollar spans 2 different classes. So let's first ask ourselves, in a frequency distribution, can there be any overlap between the classes? And if you think back to the graphs and charts video where we covered frequency distributions, you might remember that a proper frequency distribution will have no overlap. So take a look at the dollar ranges for these 2 classes. Are there any overlaps between them? There are not, and there's no gaps either. So because there is no overlap or gaps between these 2 classes are considered mutually exclusive. There is no dollar amount that could fall into 2 classes at the same time. Any dollar amount is only going to fall into one class. So in a frequency distribution, each class is mutually exclusive from all of the others. So because of that, to find the probability that the sales representative will sell between $75,000 and $124,999, what we're going to do is we're going to take the probability for that first class, which is between $75,000 and $99,999, and then we're going to add to it the probability of the second class, $100,000 to $124,999. And because these 2 are mutually exclusive, we do not have to worry about subtracting any overlap. So for the probability that the sales will fall in this class here is 7 out of 36. Class frequency divided by the total. Then we're going to add to it the probability that the sale fell in this class, which was that 9 out of 36. So 7 out of 36 plus 9 out of 36 is either 16 out of 36 or 4 out of 9, or if you want to turn it into a decimal, 0.4 for repeating, or about a 44.4% chance that the sales representative sold between $75,000 and $124,999 next month. This next one is another example of empirical probability. So what we have here is a table that gives the catalogs of types of blood, including positive or negative Rh factors that were given by donors within the last 5 days. So just to kind of help you read this table, Rh factor is either if it's positive blood type or negative blood type. So each of these columns represents the different blood types. Each row represents the Rh factor. So this 156 right here would be O positive blood. This 25 is A negative. This 184 is the total number of people who had type O blood, both positives and negatives. This 164 is the total number of people who had type A blood, positives and negatives. Now this total over here on this row, this 344, is the total number of donors who had positive blood types across, who had positive Rh factors across all of the blood types. This 65 here is the total number of donors who had an Rh factor that was negative across all the blood types. And 409 here is the total number of donors, period, across all of the blood types and all of the Rh factors. So what we're going to do is we're going to use this table to find each of these probabilities. So for number 1, we are finding the probability that the person, that a randomly selected blood donor, has either type O blood or type A blood. So since this is an or, remember only one donor is being selected, and we're finding the probability that they have type O blood or type A blood. Now, this didn't really care about Rh factor at all. It was just type O or type A. So again, you have to ask yourself, are these two events mutually exclusive or not mutually exclusive? So can a person, according to this table, have both type O blood and type A blood? So the way this is set up, and you're not going to have a blood donor that is both type O and type A at the same time. So because these two events cannot occur at the same time, they are mutually exclusive. So because these two events are mutually exclusive, to find the probability that the person has type O blood or type A blood, all we have to do is find each of those separate probabilities and add them together. So we're going to find the probability that the person has type O blood, and then we're going to add to it the probability that the person has type A blood, and then we don't have to worry about subtracting any overlap because there is no overlap. All right, so for the probability that the person has type O blood, remember this is a probability from a frequency distribution. So the probability that the person has type O blood is the total number of people who have type O, 184, divided by the total number of blood donors, 409. Then we're going to add to it, out of those 409 blood donors, 164 of them had type A blood. So when you add these two together, you get 348 out of 409. Or if you want to turn it into a decimal, it's about 0.851. So there's an 85.1% chance that a randomly selected blood donor has type O blood or type A blood. So then for number 2, we are finding the probability that the donor has type B blood or is Rh negative. So before we dive into this, we have to ask ourselves, are these two events mutually exclusive? Could they occur at the same time? Can you have a person that has both type B blood and a negative blood type? Yes, you can have a person that has both type B blood and a negative blood type. It's B negative blood. So B negative is both type B and Rh negative. So because there is overlap, because these two events could occur at the same time in the form of type B negative blood, these two events are not mutually exclusive. Because these two events are not mutually exclusive, you do have to worry about overlap. So to find the probability that the person has either type B blood or negative blood, we're going to find the probability of the first event, so the probability of randomly selecting a type B blood donor, plus the probability that they have negative blood type, so the probability of randomly selecting a person that has negative blood type. And then we're going to subtract the overlap. Remember, the overlap, the blood type where these two could occur at the same time, is B negative. So then we're going to subtract the probability that the person has B negative blood. All right, so for the probability that they have a B blood type, period, is the number of people in total who had type B blood, which was 45, out of the total 409. Then we're going to add to it the probability that they have negative blood type. So remember, the 65 is the total number of donors who had negative blood type, so that's 65, out of the total number of blood donors, 409. Then we're going to subtract the probability that they specifically have B negative blood. This 8 here is the number of people who have B negative blood, so that is going to be 8 out of 409. So then when you do the adding and then the subtracting, you're going to get 102 out of 409. Or if you want to turn it into a decimal, there's about a 0.249% chance, or almost a 25% chance, that the randomly selected blood donor has either type B blood or is Rh negative. So then for this next one, this diagram represents a breakdown of positions of the 253 players that were picked in the 2012 NFL draft. So what we're going to do is we're going to find the probability that a randomly selected draft pick is not a running back or a wide receiver. So, I mean, if you take a look at this diagram, there are a ton of positions that are not running backs or wide receivers. So instead of just finding all those probabilities and adding them together, we're going to go about this in a slightly different way. We're going to use complements. Because we're finding the probability that that a randomly selected draft pick is not a running back or a wide receiver. So the opposite of that would be the probability that they are a running back or a wide receiver, which is a lot easier to find. So that's what we're going to do first. We're going to find the probability that the randomly selected draft pick is either a running back or a wide receiver, which I'm going to just denote as RB or WR. And then what we're going to do is to find the probability that they're anything else, we're just going to subtract it from 1. Now, before we get started on this, we're going to ask ourselves, are these two events mutually exclusive? Could these two events occur at the same time? And while I am aware that you can have someone that is drafted for 2 positions at once, these are both offensive positions. While they might be drafted for the 2 of these at the same time, they're not going to play these at the same time. You know, in one play, they're not going to fill both roles. So we're going to say that these events are mutually exclusive. They're not going to play both of them at the same time in any given play. So these two events are mutually exclusive. So because of that, all we have to do is find each of these individual probabilities and add them together, and we don't have to worry about subtracting out any overlap. So we're going to find the probability that the person is a running back. Then we're going to add to it the probability that the draft pick is a wide receiver. So remember, there are a total of 253 players that were drafted, so that is going to be our sample space. That is going to be the denominator of each of our probabilities. So for the probability that they are a running back, there were 21 running backs out of 253. Then we're going to add to it probability that they were a wide receiver. There were 33 wide receivers out of 253 total players. So when we add those together, we either get 54 out of 253. Remember, it is okay to leave probability as a fraction, or you can, use a decimal point 213. But just for accuracy, I'm going to leave it as a decimal because we're not, for accuracy, I'm going to leave it as a fraction because we're not totally done with this yet. Because this was the probability that the randomly selected draft pick was a running back or a wide receiver. The question is actually asking us to find the probability that they are not a running back or a wide receiver. So to find the probability that they are anything else, we're going to find its complement. So we're going to find the probability of that running back or wide receiver, its complement, which remember is denoted by that prime notation. So because all of the probabilities in a sample space need to add up to 1, all we have to do is 1 minus 54 out of 253, and that will give us the probability that the randomly selected draft pick is not a running back or a wide receiver, which is 199 out of 253, which remember you can, let me try that again, which is 199 out of 253, which remember you can leave it like this, or if you want to turn it into a decimal, it's approximately 0.787. So it's about a 78.7% chance that a randomly selected draft pick is a running back or a wide receiver. Sorry, they're not a running back or a wide receiver. I got distracted by my glitching stylus. Sorry about that. Now with this table, and this table is available on the PowerPoint, which I have posted on Canvas. Remember, you can find all of these PowerPoints on Canvas. So feel free to, either pause the video and copy it down if you want to, or just print this slide off of Canvas, whichever. But this slide just pretty much sums together all of the probability topics that we have covered so far. So remember, we have really the two types of probability that we're going to be looking at are classical probability and empirical probability. Classical probability is the probability in theory where each outcome is equally likely to occur, and it is given by the number of outcomes in the event E divided by the number of outcomes in the sample space. Empirical probability is the probability in practice, and this is the probability that you get from either experiments, observation, etc. And that is going to be, its probability is going to be the frequency of event E divided by the total frequency. Remember that all probabilities must be some fraction or decimal between 0 and 1 inclusive. 0 is impossible and 1 is guaranteed. Complementary events, like the last one, are perfect opposites. So to find the probability of an event's complement, you just do 1 minus the probability of the event. So to find the probability that they were not a running back or a wide receiver, we did 1 minus the probability that they were a running back or a wide receiver. So that last example was an example of this in action. Now, a lot of people do mix up multiplication rule and addition rule. Multiplication rule occurs with two events occurring in a sequence, one right after the other. So the multiplication rule will deal with and. So look for the word and. And multiplication rule, what you do with it depends on whether the events are independent or dependent. Remember, events that are independent or dependent, we covered that in the last video. Does the outcome or occurrence of one affect the outcome or occurrence of the other? If the events are dependent, then to find the probability of A and B, you just do probability of A times the probability of B given A. If the two events are independent and the probabilities have nothing to do with each other, then to find the probability of A and B, it's just the probability of A times the probability of B. Now, the addition rule, which we just covered, there's only one event happening, but you're looking at the probability of one outcome or the other outcome. So you're going to be looking for the word or. So this depends on whether they are mutually exclusive or not mutually exclusive. Remember, mutually exclusive deals with could these two events occur at the same time. Now, if the events are not mutually exclusive, which means they can occur at the same time, you need to subtract out the overlap. So it'll be probability of A plus probability of B minus the probability of A and B at the same time. If the events are mutually exclusive and cannot occur at the same time, then the probability of A or B is just the probability of A plus the probability of B. So use this slide as a reference when you're studying for your first exam. All of these probability topics will be on the first exam, and you will be responsible for figuring out whether you're supposed to use the multiplication rule or the addition rule, classical probability, empirical probability. So use this slide as a reference. So that is going to be it for the probability topics that are going to be on the first exam. So that'll be it for Chapter 3 so far. After the first exam, we're going to cover a couple more topics in probability, and then we're going to start using probability in inferential statistics. So stay tuned for that video, and thank you all very much for watching. If you have any questions or have any questions about the next exam, please just email me, and I will see you guys in the next video. Bye-bye.